So today we're going to continue this discussion of power-suppressed Lagrangians, and I'll explain to you why we think of these as giving power corrections to observables. And we'll talk about a couple different observables where these specific operators are playing an important role. And then we're going to turn to the topic of renormalons, which is fun stuff. How many people here know what a renormalon is?
One.
Yeah. By the end of the lecture, you'll all know what a renormalon is. Okay, so this is where we left off. We were talking about this symmetry reparametrization invariance, and what we showed last time is that the Wilson coefficient of this operator is 1 to all orders in perturbation theory because of that symmetry. The Wilson coefficient of this operator is not, and I told you that at leading log order it would be given by some expression like this. But in general, this is just the lowest order expression, and it gets perturbatively corrected. It's actually known at 3 loops. So let's continue. We've talked about reparametrization invariance for the Lagrangian. Reparametrization invariance also has important consequences for operators. So just like we wrote down subleading Lagrangians, we should also write subleading currents. So there's 1 over MQ suppressed currents. And if you look at those currents and you construct them, then you find, again, that reparametrization invariance plays an important role. And again, there's relations between Wilson coefficients. And what happens in this case is actually that the leading order operator had a Wilson coefficient, the lowest order operator. So the Wilson coefficients of the subleading operators get related to that of the leading operator. And I may give you a problem on that on your next problem set, but I haven't quite made up my mind yet. So rather than go through that, I want to talk about some observables where these operators play a role. So we've seen one example of reparametrization invariance, and I think from that one example you would be able to do other examples. Let's talk about masses. These operators here actually have an impact on the masses of hadrons. If we think about the mass of a heavy meson H, there's a heavy quark in that heavy meson, and so we can pull out that heavy quark, and then there's some remainder. And we can characterize higher order terms in this formula. So let me first explain what this lambda bar is. Our Lagrangian here, if we're working at lowest order in the theory, our Lagrangian would be L0 of HQET plus, for the light quarks, basically just a QCD Lagrangian. So for the light quarks and the gluons. So for the heavy quark, we have HQET, and then there would be higher order terms that are 1 over M suppressed, which are the ones up there. So the question is, if we have this Lagrangian, what is the mass of a heavy state, like the B meson or the D meson or the D star? And we can characterize that by knowing the structure of the Lagrangian. So first of all, what about this term, this lambda bar? That term actually comes from these parts of the Lagrangian. So if we take these parts of the Lagrangian, we can calculate the Hamiltonian. Let me call that H0. And the definition of this lambda bar is the thing that you get by taking that Hamiltonian and letting it act on the state. So you can think that this is, if you like, you can think that this state is just an eigenstate of the Hamiltonian. You get the energy. But since the Hamiltonian has no heavy quark mass in it, what you're getting is some parameter, which is traditionally called lambda bar, that doesn't have a heavy quark mass in it. And so there's no heavy quark mass in here. So it's independent of MQ. It's also independent of spin, so B versus B star, and flavor B versus D. So whether it's a B meson, D meson, as long as we're in this limit where both the bottom mass and the charm mass are heavy, if we're thinking of this expansion, then this is a universal thing, just determined by these Lagrangians. It's traditionally called lambda bar, and it's telling you if you think about this thing as having an order MQ piece, this is the order MQ to the 0 piece. So the symmetry of the theory is telling us that this is a universal constant. It does depend on the state here, and that state, although that state could be connected to other states by spin symmetry and flavor symmetry, there was this quantum number we talked about last time, which we called SL for the spin of the light degrees of freedom, and then pi for the parity of the light degrees of freedom. So it's the same within every multiplet that we get from a fixed SL pi. But there's a different value for each multiplet. So you'd have a different value of lambda bar for the B, D, B star B than for the lambda B and the lambda C, for example. So that's this term. We can also characterize what's going on with this term by using this Lagrangian here, the L1. So at order 1 over MQ, we can figure out what kind of contributions to the mass we're getting. H1 is just minus L1. You can think of it now perturbatively. So that just flips the sign of what we had before. And we get two parameters from taking matrix elements here. They get the following names. And let me just do everything here in terms of, it's not totally crucial, but I'm going to, it's a little easier to interpret certain things if we work in the rest frame, so I'll just work in the rest frame. So if you work in the rest frame, you should just think of this as like giving some kind of measure of the kinetic energy that the heavy quark gets wiggled by, and that's called lambda 1. This, again, is a matrix element that doesn't know about the heavy quark mass, and the heavy quark mass is an explicit MQ. So this guy has dimension 2, if you work out the dimensions. And then you can do the same for the other operator. And here you have to think a little bit harder. And if you think a little bit harder, you can characterize how what the coefficients are for different spins. So there's some Wilson coefficient. And then we have this operator. And this here is like sigma dot B. I told you that before. And so you should think of what's going on here is you have sigma, which is giving the SQ, and then you have a B field, and then it's a question of what vector could be left over that the B field can know about, and it's basically SL. So this guy here is leading to the SQ. And this guy here is leading to the SL. And so that's where this SQ.SL comes from. So you can think about other possibilities, but you have to have the right symmetry structure under time reversal and parity and things like that. And that forces you to use a spin here for the B and not something like the V. So this SQ.SL is something that you can write out as remembering the definition of it and its relation to j squared, we can write out that factor like that. And then we can derive here how this lambda 2 contributes to the different states, because we have a different contribution for the B and the B star from the lambda 2 guy, because it was violating the spin symmetry. So the lambda 1 guy is going to violate the flavor symmetry. That's this 1 over MQ. And so charm quarks, charm mesons and bottom mesons will get different contributions from that. They have the same lambda 1, but they have a different correction because it gets suppressed by a different factor. And then, again, for the lambda 2, lambda 2 is a little bit different because it actually has mu dependence. I didn't say that quite right. So it actually has MQ dependence because the coefficient here has mu dependence. So this operator doesn't have any MQ dependence, but the coefficient does, remember. The mu dependence cancels, and there's a leftover MQ dependence to the lambda 2, but it's logarithmic MQ dependence, if I define it this way. So that's why I wrote MQ there. So you could, as we talked about last time, you could sum up the logs, the large logs, and have this guy, you could resum logs if you want. So you could think of these as even resum logs inside this lambda 2. So if we ignore those logs, or we imagine that we resum them, and we just look at the remainder, then we have expectations based on power counting for how big these things are. And we just expect that they're both given by the dimension. And the only dimensionful parameter around is lambda QCD, because the MQs can only occur in logarithms in the Wilson coefficient and nowhere else. And these are non-perturbative parameters. Lambda bar is also a non-perturbative parameter. These ones have a little more dynamics in them. So then we could go out and write for our states the results by putting these things together. So we'd have M capital B is M little b plus lambda bar, lambda 1 over 2 M little b. And if we go through the spin structure there, we get a 3/2. And then lambda 2 logarithmic MB dependence over MB. When we start with the B star, the first 3 terms are the same, and then this guy comes in with a plus, and it's lambda 2 over MB, or 2 MB. And then the D states are similar. M charm, lambda bar, lambda 1 over 2 M charm. And then these 2 terms again, same spins, so it's lambda 2. And the only difference is now we're evaluating the lambda 2 as logarithm charm dependence. Okay, so there's some formulas that are correct, actually, including all the way up to 1 over m corrections. And you can see that there's still sort of a structure to these things. This is a universal correction for all of them. These corrections are universal between B and B star, and so the splitting between B and B star is just given by this lambda 2. That's what causes the states to split. So up to that level, they're the same, and that's why the B and B star are very degenerate, and the masses are very close. So you can form combinations to cancel things out. So you can take a kind of spin averaged mass, where you take 3 times the vector plus the scalar, divide by 4. And if you do that, then you're canceling out the lambda 2. And then you can also form differences. So if you looked at MB star squared minus MB b squared, then the only thing that's causing a difference is lambda 2. Numerically, this is 0.49 GV squared. And from our formula up there, it's 4 lambda 2 of MB. So something like 4 times 0.12 GV squared. So that's the value of this lambda 2 is 0.12 GV squared, which is about lambda QCD squared. So our dimensional analysis is working. And then you can do the same thing for the d meson. Everything here works beautifully, actually. Oops. Extract the value of lambda 2, and you see there's a slight difference, because that difference can be attributed to the logarithms. So if you take lambda 2mb over lambda 2mc, then the only thing that differs is the Wilson coefficient, so that's something you can predict. So experimentally, if you take the ratio of those two things there, you get a prediction like this one. And if you plug in theory, like leading log RGE, you're getting alpha S of MB. Oh, sorry, trying the numerator. And this is 1.17. So that's for 3 light flavors, just the right thing to do for the beta function. So it's not so bad for a leading log prediction. That's kind of the accuracy you would expect. All right. So we're really understanding quite a bit from our construction of this effective theory about the states, and even make predictions for the ratios of the mass. This divided by that is something perturbative, which is kind of non-trivial. Perturbative up to the order we were working, there would be corrections if we continued in our series here. There could be some non-perturbative corrections, but up to 1 over m, the ratio of this to that, which is what I wrote over there, is perturbative.